Hey.
Hey, sorry for a stressful. Usually just lets people in, and asked Alex for the password, and he's like, "Oh, I'll just automatically sign in." I was like, "No, I need the password."
Yeah, that's
Sorry
okay.
about that. I've
No,
never had to
that's
go through
okay.
that.
Can you hear me okay?
Yep, you're all good.
Cool, cool. Let's take this blur off. And then just to share quick, I want to make sure that you don't see my notes. How does that look?
Good. I only see your presentation.
Okay. And then where's the chat? I don't know. If there's anything in the chat, you can just
Yeah, and I'll have them, like, if they have any questions, use the Q&A function just so it doesn't get lost in the shuffle, and I'll explain all of that too.
okay.
And then I'll just monitor it and just see if there's any questions while you're presenting.
Okay, that sounds good. I need to pause my notifications. My dog doesn't go crazy because sometimes she like barks at me when I'm talking on the phone, and I'm like, okay, now's not the time.
Yeah.
Not the time.
Yeah, I know. I like just texted my family. I was like, do not come into my room for the next hour.
Right, I know. It's like my wife is working. Should I keep this light on or off?
Either is fine.
Okay. I like was talking to my wife this morning, and I was like, "Are you working from home by chance? Can you like watch the dog?" And it was a no.
Yeah, no, it's working from home. But I mean, everyone's in the same boat.
Yeah, exactly. I know that's the thing. It's like if I hear someone's like baby cry or something like that, I don't think anything of it. You know, like it's not a big deal.
Yeah.
But for me, I'm just like, oh, I don't want any disturbances.
Yeah. All right. I'll see a few people join in already. Thank you all for just funneling in. We'll get started at the top of the hour, so just chill for now. Me and Joe are just chatting about working from home.
We're all in it together.
Yeah.
And Katie, do you want to start right at the top of the hour? Or do you want to give it a couple minutes for people to join in?
I'll probably give it a few minutes. Yeah, I'm just about to post in the LinkedIn event just so everyone can see that we're about to start.
Perfect.
Sweet. I just put it in the LinkedIn event. We'll just allow for a few more minutes before we get started today. So just everyone hang tight and I'll do some introductions. Give it another minute or so, just to have some people have the chance to funnel in before we get started.
Sounds great.
All right, I'll just start by kicking off with some introductions. Thank you everyone for joining today's webinar, How to Leverage Data Science to Predict Customer Outcomes. I'm your host, Katie Zwiefel, and I'm with Tessellation and Data Coach. Just a few housekeeping items before we get started in today's presentation. Please, if you have any questions throughout the presentation, just use the Q&A module. This way, we're able to make sure that any of your questions don't get lost in the shuffle if you're using the chat box. Use the chat box to introduce yourself. We would love to know your name, where you work, and what position you hold. This is a great way to network as well. Feel free to drop your LinkedIn profile in the chat, and just be mindful to be respectful of one another and just have fun during the webinar. And then before we get started, we just have a quick message from our sponsors, Tessellation and Data Coach. Tessellation is a modern analytics consultancy. We enable and manage organizations, analytics, and self-service teams by educating people, optimizing technology, developing world-class products, and providing sustainable results. And Data Coach, where most analytics training programs lack depth, Data Coach provides wisdom. Our modern curriculum is unparalleled, comprising video lessons, hands-on exercises, and a capstone project designed around your company's data. Data Coach also offers a truly premium service, one-on-one coaching. I would also love to introduce our speaker of today's webinar, Joe McFerrin. Joe has been a consultant for 4 years, undertaking various roles as a business analyst, project manager, scrum master, data analyst, and developer, and he has a strong interest in data science and how to apply data best practices to our clients. As a consultant at Tessellation, Joe interacts with our clients to understand their data needs and problems, help craft a solution, and empowers the client to own the end product so there are no gaps in the handoff process. All right, without further ado, Joe, please take it away.
Thank you so much, Katie. Hey, everyone. Like Katie said, I'm Joe McFerrin. I know it says Stephen McFerrin on there, but I go by my middle name. So today we are going over some data science for business problems, and we're going to be using data science principles to predict customer outcomes. So just a brief agenda. I'll do just a brief welcome and introduction, Tessellation's approach to data science for business problems, get down to the model that we're going to be going over today, which is what is KNearest Neighbors, go over bits of the code, some of the results and error metrics, and then talking about other business applications. So again, I'm Joe. I'm a consultant in the data science practice here at Tessellation. I started my career as a research scientist, performing academic research at the Masonic Cancer Center at the University of Minnesota here in Minneapolis. And I specialize in molecular genetics, molecular biology, and cancer biology. Got experience in data science, data visualization, data strategy, cloud architecture, and computing. Like Katie said, I really love working with clients, helping develop a solution, help being part of that, and then of course the handoff process to make sure that it's a maintainable and scalable solution. I've worked in healthcare, manufacturing, 3D printing, consumer packaged goods, food and beverage, legal services, a little bit of everything, but with my background, I certainly love working in healthcare, and that's always been an interest of mine. So today we'll go over how data science can be used at your company, what a classification model is, we'll view parts of the code, and then discuss how we can relate this back to predicting customer outcomes. So first, our approach to data science at Tessellation. We really see data science as something that can certainly be applicable for a lot of people, can be applicable for a lot of teams, but we see a couple of things to be mindful of when creating a data science solution, implementing a data science solution, scaling a data science solution. So there's a number of things that we really like to be mindful of. The first one is having human-centered and human-centered design, using design thinking principles, and really building a solution that is intuitive, user-friendly, and most importantly, interpretable. It's honestly pointless if you have a data scientist that creates a model but no one knows what the results say. You can have the most amazing model, but if no one can interpret the results, know what the results mean, and then apply those results to help solve a particular use case or business problem, it doesn't really matter. Starting small and failing fast. I think we've all probably heard something along these lines, but we always really start small to make sure that the data science solution proposed is feasible, because there are some times that if you look at certain problems or certain use cases, maybe data science actually isn't what we're looking for. It can allow for rapid testing, rapid ideation, definitely some road mapping. And that really means starting with a proof of concept or an initial project. You don't need a $1 million initiative to start using data science at your company. Iteration. If you've ever worked in an agile workspace or in an agile format, iteration means being okay with your minimum viable product in that first MVP and building from there. You don't have to have the perfect model. You don't have to have the perfect results the very, very first time. It's really iterating and building on things and getting better each time. So it's using those agile best practices, and then also some practices from the CRISP DM industry standards, across industry standard process for data mining. That's really using that business and data understanding that leads to data preparation, data modeling, data evaluation, and then eventually deployment of the model. One more thing is building to scale. So longevity and sustainability is always a big thing as well. Making sure that when handing the solution to the customer, they can maintain it and it's something that they can use moving forward. We never want to create something that's so meticulous and so niche that it requires a consultant to come in, hold on to that solution and be there for forever. We want to make a solution that we can hand off with a proper documentation, that it's simple enough to get the job done, but at the same time, make sure that we get the results that we're looking for. And then finally, transparency. We never want to hide anything or keep anything as a secret or anything like that. We always want to make sure that we can hand this off to our client, make sure the client can use it, and make sure that it's maintainable and sustainable. So data science for business problems. It can be a really powerful way to solve business problems, but again, it's not always the right solution. We kind of ask ourselves a couple different questions on whether data science, if this application makes sense, and if it's something you should move forward with. So what's the core problem? Do we want to predict if something's going to happen? Are we trying to categorize something based on unlabeled data? Or do we want to find out how likely is an event to occur? If the problem is, how much money did we spend last month? We obviously don't need to invest in a data science pipeline to predict something that we already know. But you can also ask, what data is available? What are the biggest impediments to solving this problem? If the data is not available, it might be a data engineering problem where you have to work with your DE teams to better understand where the data is coming from or how to access it. If there's a huge roadblock, you can't move forward with the solution. So it's always thinking of it as a holistic approach rather than just seeing, we have a bunch of data, we want to have a cool machine learning model, and let's push it forward. So definitely a couple of questions to think about and to ask yourself there. Excuse me. Additionally, what is a classification model? So as we talk about data science and applying data science to potential problems, here we can get into our KNearest Neighbors and a little bit more specifics into our classification model. So what is a classification model? Classification uses the characteristics of a variable to assign the data point, a class, or a label. So for example, you can use a classification model for fraud detection. So fraud detection services can be used as a classification problem because the transaction is fraudulent or it's not. If a credit card transaction goes through and it's at an interesting time of day that's not necessarily associated with this individual person. If it's an amount that's much larger than the average spend. If it is processed in a country that the user typically doesn't run their card in, all of those variables could contribute to a transaction being identified as fraudulent. So with classification models, they're really considered supervised learning in that the model uses labeled data points to predict an outcome. So there's supervised learning and there's unsupervised learning. So with unsupervised learning, you may have something like clustering, where you can run the model to see natural groups or clusters and then assign a label from there. There's a very popular data set that people use often. It's the IRIS data set from UCI. That's a great data set to use if you're looking at k-means clustering, or if you're looking at other classifications that you'd like to do. And from there, you can put data in, put it into the model, and it'll develop some natural clusters based on that data. Whereas with here, this is a supervised learning model. We know the label of our data point. We know that in this example, it's a man, or it's a woman from the United States. Put that into the model, and then you have your output. So we can use test data to train a model to understand what are the characteristics of, for here example, vegetables or groceries. So this is one example of classification. We have our independent input variables. We have our food items, our vegetables, and then we also have our groceries. We want to put that data into a classification model, train it using data that we already know is, say, vegetables and say groceries. And then from there, you can get your categorical output value when you, or variable rather, when you use your test data. So you run your test data through the model, and then from there, it makes its best approximation based on these variables as to what a vegetable may be, or what something is classified as groceries. So basically, if we have no idea what either of these items were, and the model would give us common clusters, that would actually be an unsupervised learning model, because we would be using unknown, unlabeled data. So from classification, we get into K-Nearest Neighbors. What is K-Nearest Neighbors? So just to take a step back quickly, most data science models that are used to solve business problems are classification models, because most business problems require making a decision, right? You can use a classification model to potentially say, is this customer at risk for canceling their cell phone plan, yes or no? You could take a look at manufacturing logs from a piece of equipment and see and predict, will this piece of manufacturing equipment fail? Yes or no? So with that being said, K-Nearest Neighbors is a supervised machine learning model, what we just went over using labeled data, that can be used actually both for classification and for regression, but it's most commonly used for classification. Supervised models really rely on labeled data to predict an outcome. KNN in particular, it's really easy to interpret the outcome, and we'll go over that in a little bit here. It has a relatively quick calculation time, and I say relatively because it depends, of course, on how many metrics you have, the size of the data, the dimensionality of the data, things like that. And thinking about, what does your data set look like? And if it's a good use case for KNN, and we'll go over that in a little bit, it can have a very quick calculation time. And then, of course, there's a large predictive power to take labeled data, run it through our Knearest Neighbors model, and then from there, it can help predict different things, whether it's a yes or a no. And I've got a couple examples with blue or red, things like that. One thing is that KNN is a fairly memory intensive algorithm. Since it's classified as a memory-based algorithm, that's to say that it uses a lot of memory when running, but at the same time, again, depending on the data set, the size of the data set, the dimensionality of the data set, it can be a very, very quick model. And additionally, as you'll see, it's only just a few lines of Python just to run a K-Nearest Neighbors model. It's also identified as a lazy classifier. If anyone's familiar with that term, it's a lazy classifier rather than an eager classifier, in the sense that it memorizes all of the training data instead of learning a function. So for example, with the regression, if you have a linear regression, it's going to make a line. You have an equation associated with that line that you can use to plug in data sets. K-Nearest Neighbors doesn't do that. It actually memorizes all of the training data from the training set that you put into the model. And then from there, it can make predictions based on memorizing that training set rather than establishing a function. So just some examples here, and I think this is a really, really great way to visualize what K-Nearest Neighbors does. So in K-Nearest Neighbors, the K is just a variable. Sometimes if your K value is 1, you can see it written as 1 nearest neighbors, 5 nearest neighbors, 100 nearest neighbors. But here on the left, we can see that with one nearest neighbors, all of these are going to be identified appropriately, right? You can see there's little bits of blue within the red. There's some red within the blue. That's because with one nearest neighbors, it's always going to be perfect. There's no errors because it's identifying itself as its own closest neighbor. So you're never going to have an error. Whereas when we up this to 3, you can start to see that those boundaries kind of smooth out a little bit. Some of the areas close in because now we're taking the 3 nearest neighbors to one point. And for that red point, for example, its nearest neighbors instead of itself, now it's blue. So we're classifying that as a blue point. It's erroneously classified as a blue point, but still it's blue. As we move up to 5 and to 7, you can really see that border start to smooth out a lot. But as a result, as you increase that K, you can start to introduce some errors. So if you look at K equals 1, all of those blue dots within the red are classified as blue. Some of those red dots within the blue are classified as red. If you look at K equals 7, you can start to see there's 4 blue dots that are closer to red that are in that red classification. And that's because if you look at the 7 nearest neighbors for that point, which 7 nearest neighbors, what color are they? In this case, it's going to be red. Conversely, you look at some of the red ones in the blue, the 7 nearest neighbors for some of these red points are very clearly all blue. And that one's going to be classified as blue. So this can really show how these predictions can vary and change due to the selection of a K value. And it's not always as simple as, okay, let's add K nearest neighbors equals 1, call it a day, and take the results from that model. One thing to point out too is that K nearest neighbors isn't a great option for really high dimensionality data. So if there's 1,000 columns or something like that, as so many dimensions get added in, it can really kind of blur, and the nearest and the furthest neighbors start to kind of seem the same. So it can be really difficult if you have very, very high dimensionality data, say medical data. It's not always the greatest. One thing with K-nearest neighbors too that you can do is you can standardize the data. So it's standardizing the data. It's making so that that data is more a relative value. So if you have a large discrepancy between data types, for example, maybe one is kilometer and one is centimeter. The kilometer values are inherently much, much larger. So those would potentially sway some of our results. You can standardize the data and then have everything be kind of on that equal playing field. Alternatively, since KNN isn't a great option for some of these data sets, you could also use, say, k-means clustering. If you're looking for a clustering model, you could use support vector machine classifying, or classifier rather, if you have really high dimensionality data. I won't get into these today, but happy to talk about any of these if you'd like to reach out on LinkedIn or anything like that. So what is K-nearest neighbors? Still, the K, like I said, is it's a variable. It tells you how many of a value is closest to the point of interest. If we look at this graph on the right-hand side here, we can see error rates and K. This is called the elbow method, and you can write a for script in Python, and there's a ton of documentation on this out there on the internet. But you can see our predictive error on our test data. It potentially starts out really high, and it bottoms out. And where that arrow is showing is that might be the best K value for us. So whether that's 100, whether that's 5, with that curve, it has the lowest amount of errors there. And like I pointed out earlier, K equals 1, 0 error. The training data has been memorized, and each point to itself is its own closest point. So it's going to be classified correctly. As you can see on the left-hand side from the previous slide, each one of those dots is classified as its own color. As the number increases and gets larger and larger and larger, those boundaries really smooth out. As the number approaches, essentially approaches infinity, we would only see all red points or all blue points just because that number gets so large with K-nearest neighbors. So your K value will change how many neighbors a point will consider to make a guess as to that point's value. So in that sense, again, like I was saying, you look at a point, you can draw a circle around that point and say, okay, what are the 5 nearest points to the point of interest? If there's 3 of them are blue and 2 of them are red, by majority, we would classify that as blue. If you have 15 and you take a look at that and you see 10 of them are red and 5 of them are blue, we would classify that point as red. And then again, you can use that k-value curve shown here on the right to see roughly where the fewest errors may occur. So even though that line really bottoms out, you don't necessarily know exactly what number. So it's always best to kind of play around with that, see what the results look like, see what your error metrics look like, and then you can go from there. So this is an introduction to the data set that I had used. So this data set I used from Kaggle, which I'm sure many of you are familiar with Kaggle. The data is 15 columns by about 32,000 rows. So relatively speaking, it's a fairly small data set. As you can see below, it has values like age, work class, education, marital status, a bunch of other things. And the problem that we want to predict here is, can we predict if an individual makes more or less than $50,000 annually based on these various attributes? So as you can see, for index value 0, we have someone that's 39 years old. They work in the state government. Excuse me, the final weight is a continuous variable that represents basically how many units in the target population this may be. So this is just an estimate by the data provider as to how many people this particular row may represent. Their education, they have a bachelor's degree, 13 years of education, they've never been married, et cetera, et cetera. So from here, what we're doing basically is taking each one of these attributes, kind of combining them together through our KNN classifier, and then making a prediction based on these values. Does this person make more than $50,000 a year or less than $50,000 a year? So this is a screenshot from my Jupyter notebooks using Python, saying we're going to import the data into a data frame using pandas. And then to see if the import was successful and make sure that the data came through, we're going to be using the .head call on our data frame. So I did pd.read-csv from my desktop from a folder there, and then showing the head of the data. Success, we see the first five rows of data. So the data set was fairly clean. There are a few things that I had to do to clean up the data set. There's a couple of unknown values. So when you're looking at a large data set, or frankly, a small data set, you always want to look at, are there null values? Are there unknown values? Is everything in the same, say, string format? Things like that. So I used a couple of different imputation techniques. I think for, it was education and occupation. I used mode imputation, so taking the mode of the data set and imputing the value from there. There's a few other options, of course, but this is one that was fairly simple and straightforward. And then running this model on this particular data set, I really did it just because this can be applied to a lot of different business problems. So as we go through this, you'll see that although this may not be particularly related to a business problem, we could apply this technique to a lot of different use cases. So with the code, I'm not going to go over my notebook line by line. I don't think anyone wants to see that. But one thing is that we established our outcome variable. So that was our yearly salary. We're using all these different metrics to see, okay, does this person make more or less than $50,000 annually? So with our outcome variable, our yearly salary, what we're trying to predict, we're then going to use everything else beside that as our predictive variables: age, sex, race, occupation, education, et cetera, et cetera. So here, our dependent variables income, our independent variable are everything beside income. So the way I did that in my notebook was I said, X equals the column income, and then Y is the data frame, but just drop income. So everything beside income. So we assign these to X and Y. We split using something called train test split. So that is something from scikit-learn, which is a really great package that you can use for many different data science techniques. Train test split is great because it splits the data set for you. In this case, I kind of use the rule of thumb using 20% of the data to train, 80% of the data to test. And that's all pretty much done with that package in scikit-learn. From here, I decided our k value, just for simplicity's purpose, or for simplicity, I used a technique that some people use, which is the square root of the number of records in the testing data set. So I believe that ended up being 161, and then ran the model using our training data. So I have a couple of error metrics, which I think are really important with models and data science in general. Just being able to say, what's wrong with this model? What does it do well? How can we improve it? And ultimately, how can we use this to inform a business decision? So continuing on with our data set, I ran a couple of things for some kind of exploratory data analysis, looking at various correlations, some different box and whisker plots, for example. But one thing that I really like doing initially is using a pair plot from Seaborn. Seaborn is another data science or data visualization package rather in Python. And we can use Seaborn that has an alias of SNS, as you can see up there, and use our pair plot on our data frame. So we use this to show all of the different, or a couple of different variables here. So we have age, we have that final weight, we have education, I think it's work hours, and then capital gains and capital losses. So if this data set was much larger, we could certainly narrow it down and subset the data and then use a pair plot from there. But I just decided to run it based on the data frame. And one thing that's kind of interesting with the pair plot is that when a variable is presented with a correlation against itself, it actually just gives a histogram. So then you can see the distribution of the data. So for age, you can see it kind of is a bit of a younger crowd here. With some of our other variables, you can see that most people have little to no capital gains, little to no capital losses, and then the vast majority of people work 40 hours. Is this all very important for our purposes? Maybe not, but it's always something to look at in terms of just exploring the data. Are there any extremely apparent correlations? Because that could either give you some insights into the data, or it could say, okay, well, clearly this variable is already dependent on another one. So talking about variable selection and error metrics, with this one in particular, like I said, I decided to simply use all of the predictors in this data set. But we could have chosen to use a various combination of them. We could have chosen only men, only women, maybe people over under the age of 25, maybe only people in the United States, things like that. So if the data set was really big and we knew everything about the customer, say is a marketing analytics problem, and we know location based on IP address, we have a ton of clickstream data, we have duration data on different pages, we have number of page views, we have, you can join that data with other information about the customer. That could be hundreds, if not thousands of columns wide, if talking about a regular data frame like that. So you may want to narrow it down. And then talking about error metrics, again, this is something that is really important for understanding how well a model does. So it's not only about accuracy, we'll get into that, but you can also see things like precision, sensitivity, specificity, and then seeing false positives, false negatives, things like that. So there's certainly other error metrics like F1 score that take in precision and recall together, root mean square error, which really just shows the difference between values predicted by a model and the actual value. So it's the error between those 2 points. But here I chose a confusion matrix just because I wanted to see how the data was labeled. Since this was a classification problem, I wanted to see how many were labeled correctly, how many were labeled incorrectly, and then false positive, false negatives, things like that. One thing to note too is that oftentimes you'll hear a type 1 or type 2 error. So false positive is a type 1 error, and that's something that's identified as positive when it isn't. And then same thing with the false negative. It's type 2 error. It's identified as negative when it isn't. So here, this is just a snippet of the code I used. So here I wrote out that our classifier is KNearest classifier, and the number of neighbors is 161. Again, that's just based on the square root of the length of the training set. And it's really this simple. It certainly can be a lot more complex, but for this example, we just have our Y prediction, and we're going to predict that based on the testing data from X. I wanted to print the classification report here based on how the Y test and the Y prediction compared, as well as a confusion matrix, like I said, about our test and our prediction from our Y values. And remember, we're seeing how accurate is someone to make more or less than $50,000 annually. So then here, I also imported accuracy score from SALearn, and then printed the accuracy of the model and the accuracy score. So there's a lot to unpack here. So we'll spend a couple minutes talking about what all of this means with our classification report, and then going over our confusion matrix as well. So here you can see we have true label and predicted label. This is our confusion matrix. I used color to just add another bit to see number of counts of records. And you can see for our true label, less than $50,000 annually, right? And our predicted label, less than $50,000 annually. This is a true positive. So we had 4,943 records that were actually someone making less than $50,000. And we predicted it correctly, that they made less than $50,000. Conversely, we have a true label of less than $50,000 annually, right? But our predicted label was that they made more than $50,000 annually. To see 2 here is actually great. I wasn't expecting that. But looking at true label of greater than $50,000, this is a predicted label of less than $50,000. That's quite a few. So even though this person made more than $50,000 annually, the model predicted that they made less than $50,000 annually. That's okay. And then additionally, last, we have our true label of greater than 50,000 and our predicted label of 50,000. So this is a true positive here. Well, technically it's a true negative when thinking about positives and negatives, but we have 132. So looking at this, we have precision, recall, our F1 score, and our support. Support is just the number of occurrences for each class, for each one of less than or greater than 50,000 annually. And we can see a few things here looking at this classification report. So we can see that the model does kind of a poor job at identifying those that make greater than $50,000 annually. There's only 132 that were accurately predicted. We can also see that for those positively identified as greater than $50,000, our predicted labels, so these 2 on the right-hand side, it's pretty good. We only had 2 that were incorrectly labeled as making more than $50,000 annually. Right here, if we go into precision, that comes from taking our true positives, dividing that by our true positive and our false positive. So we want to see, how many, we want to see all the relevant values. How many were predicted positive, and of all of those that were predicted positive, how many were actually correct? So we get a precision score of 0.77. For our recall, that comes from our 4,943 plus the 2 in the data set. And then that shows us all the relevant cases there as well from the positive labeled outcome variable. So there's a couple of things that we can see here between some of these scores. We can see that our recall is pretty low for greater than 50,000. And then our F1 score that takes precision and recall together varies quite a bit. But we can see that for at least the folks that make less than $50,000 annually, we can really tell that it does a pretty good job. So this down here shows our confusion matrix. I just put it into a little bit more of a readable format. And then the accuracy of the model we can see here is about 78%. So that's pretty good. Not everything is always going to be perfect, but it's pretty good. However, some people would say, okay, accuracy is the only thing that matters. It's 78% accurate. What the heck? What's going on here? But that's not the only thing that we really want to focus on, right? Because accuracy isn't the only important thing when looking at a data science model. So imagine if we use accuracy as a measure of identifying a very, very rare disease or condition. So say if we look at the population of the United States, we have about 329 million people, and say that we only have 10 cases of this very rare condition. If we were using a model, we could label all 329 million, including the 10 that have this condition. We could all label them as non-carriers, and our accuracy score would be 99.999%. That would look phenomenal. But if you look at some of the other error metrics, like precision and recall, they would be 0. Because in this case, if all of them are identified, 329 million people, and we don't have a single true positive, both those precision and recall values are going to be 0 because there's going to be a 0 in the numerator in that equation. If we identify one person as a non-carrier, we have a precision score of 1.0 because we have one true positive. But we're going to have a very, very low recall score because there's a ton of false negatives. If we identify all people as having this rare condition, we'll have a recall of 1.0 because we'll catch every person with this condition, right? That we'll catch all 10 people out of 329 million, but it'll be incredibly, it won't be precise whatsoever because we've identified everyone with this condition. So there's a trade-off between precision and recall. And for this example, we'd probably want to have recall as close to 1 as possible because we want to identify all of the relevant cases. If we have recall very, very high, our precision could be a little bit low, but again, there's going to be a trade-off, and if one increases, the other is going to decrease. So we can stand a relatively low precision, since in this case, a false positive simply means that a person that doesn't have the disease, that would be uncovered with, say, further testing. But conversely, if it was the other way around, and we identify everyone as being non-carriers, those 10 people would never be identified as having that condition. So there's really a trade-off between precision and recall, and that's where our F1 score comes in, is that F1 score can be used to find that optimal blend of precision and recall. But going into the specifics and deep diving into that, that's for another webinar. So talking about that precision and recall, here we can see that some of those start to make a little bit more sense in that we're looking at all of the relevant values versus the percentage of values that are true positives and false positives, or true positives and false negatives. So this can really be used for a lot of other business applications. So classification models, they can be applicable for quite a few things. So a model like the one we went over can provide really actionable insights to follow up with some of your customers. So say a customer is identified as one that might cancel their subscription in a month. If you can predict that ahead of time, maybe you reach out to them and you give them a free coupon for 3 free months of your subscription service. And you could potentially keep them as a customer because now they see you as a great customer or a great company to work with, and they see the needs of the customer. You could see if a piece of machinery is going to be identified to fail in the near future by looking at usage logs, maybe some temperature gauges. If you can see this machine runs all day, every day, and the nozzle that extrudes our 3D printing material is much hotter than all of the other ones, you can do some preventative maintenance to minimize downtime on that that piece of manufacturing equipment. And then you can really minimize the loss of production for that piece of machinery in your company. Another thing is, say if a holiday season is going to be larger than usual, based on the fact that maybe everyone was inside for a really long time. Maybe the economy is really good and people are spending their money. Maybe the weather for this holiday season is going to be warmer than normal and people want to go shopping and be outside. Maybe you can adjust your production schedule to meet that incoming demand. Maybe that's something that you could apply that with, or maybe a prediction model could be used elsewhere. So I think there's really a lot of different business applications that you can use and apply this K-Nearest Neighbors to. But I think at the end of the day, it's really identifying the data, creating the model, and then from there, once you have your output, you can use that as a POC. So say, again, going back to the very beginning, you don't have to have a huge project and a huge initiative to use data science principles in your business or to solve a business problem. You can use this model as a POC if you want to put flat files into it and maybe run this weekly or something like that. You could productionalize this model in a cloud provider like AWS, GCP, Azure, and you could feed data in at regular intervals and constantly have this model putting out predictions. You could feed data into this model and connect the data output to a data viz platform like Tableau and have that run on a weekly basis and have a very simple Tableau dashboard that you can present to your executives and say, based on a variety of factors, we're predicting that X% of our customers may drop. So let's lower our prices or something like that. So I think there's countless business applications that you can use a model like this for, again, whether it's a POC, whether it's a large scale initiative that you'd like to productionalize. But if you have a question, or if you think you may have a business problem that we at Tessellation can help you solve, please feel free to reach out to myself, reach out to Adam Luckroth. His information is in the next slide. Or you can reach out to Katie here on the call as well. And we'd be more than happy to have a conversation and see what we can do. So with that being said, are there any questions? I know that's quite a bit of information and material, but happy to answer any questions.
One that came into the chat. As a freshie in data science, any best practices that you would use on how to limit the number of false positives in your data sets?
I think there's a number of things that you could do in terms of limiting those false positives. I think it really comes back to choosing the appropriate k-value. So like I was saying, there's a ton of documentation on how you can write a pretty brief for loop in Python that can enumerate through a number of different values. And then that will create that elbow curve or elbow graph that we saw, that you can choose that right k-value for your KNN model. Of course, it's not going to be perfect. It's never going to be perfect. But I think that's kind of the first step in understanding, okay, this is the appropriate value. This is how we're going to minimize our errors, not necessarily completely reduce them, but certainly minimize them. For the person that asked that question, reach out to me on LinkedIn. I'm happy to provide some resources and talk a little bit more about that once we can have maybe a larger conversation.
Great, and I also put it in the chat, the links to everyone's LinkedIn's as well. So feel free to reach out to us on there. If there's any other questions, or Joe, if you're ready to wrap up, I can conclude our webinar.
Yeah, certainly. I just wanted to say thank you. Certainly keep in touch. My LinkedIn's here. Just you can look up Joe McFerrin. I'll pop right up. So If you want to search me up on LinkedIn right now, feel free to do so, request me, and always happy to have a conversation.
Great. Well, thanks, Joe, for a fantastic presentation, and for all of you that attended today. Again, please do not hesitate to reach out to Joe, or Adam on LinkedIn. As I mentioned, I dropped all the information in the chat. If you'd like to refer back to this webinar at a later time, the webinar recording will be emailed to everyone by the end of tomorrow. Also, if you enjoyed today's presentation, please check out our upcoming webinar on October 18th. It is Do More with Data, an Introduction to Tableau CRM with Tessellation consultant Alex Carter. Well, that is all for today. Thank you to everyone that attended this webinar, and we hope to see you at upcoming events. Thanks, everyone.
Thanks, everyone.